Hello, young chemists. Have you ever wondered why sodium reacts explosively with water or why gold stays shiny and untarnished for years? At the heart of every chemical reaction is an atom's restless search for stability. Most atoms, as they exist in nature, are not stable, they're constantly seeking a way to become more balanced, and they do this by combining with other atoms. If you look at noble gases like helium and neon, you'll notice something special. They hardly react with anything. Their stability is legendary in the chemical world, and it's all thanks to the arrangement of their electrons. Atoms with incomplete outer electron shells are much more likely to participate in chemical reactions. It's like they're hungry for electrons or eager to lose some just to get into a safer, lower energy state. So, when you see fireworks exploding or iron rusting, remember it's all driven by the atomic quest for stability. Let's look inside the atom for a moment. Electrons move around the nucleus in layers called shells or energy levels. Each shell can hold a fixed number of electrons as described by the 2n squared rule, where n is the shell number. So, the first shell, K, holds 2 electrons, the second shell, L, holds 8, and so on. The outermost shell is called the valence shell, and its electrons are known as valence electrons. These are the key players in all chemical activity. Atoms are at their most stable when their valence shell is either completely filled or completely empty, just like the noble gases. Take sodium, for example. Sodium has 1 electron in its outermost shell. Chlorine, on the other hand, has 7. Both are desperate to reach a more stable state, so they react together to achieve filled valence shells. Now for one of the central rules in chemistry, the octet rule. The octet rule says atoms combine in such a way that they attain 8 electrons in their outermost shell. This is called a noble gas configuration because all noble gases except helium naturally have 8 valence electrons. Atoms may lose, gain, or share electrons to achieve this octet. When they do, they become much more stable and less reactive. Let's see some examples. Magnesium loses 2 electrons to become magnesium 2 plus, written as Mg2 plus, achieving the electronic configuration of neon. Oxygen gains 2 electrons to become oxide 2 minus, written as O2 minus, achieving the electronic configuration of neon as well. The octet rule is the reason certain combinations are so common and why some elements are more reactive than others. They're all trying to achieve that magic number 8. So, how do atoms actually reach the octet? There are 3 main ways. First, by losing electrons, atoms become positively charged ions, cations. Second, by gaining electrons, atoms become negatively charged ions, anions. Third, by sharing electrons, atoms form covalent bonds. Let's walk through a classic reaction. Sodium reacts with chlorine to make table salt. Sodium, or Na, loses 1 electron to form sodium plus or Na plus. Chlorine, or Cl, gains that electron to form chloride minus or Cl minus. Together, Na plus and Cl minus combine to form NaCl or sodium chloride. In covalent bonding, like in a hydrogen molecule, H2, each hydrogen atom shares its single electron. This way, both hydrogen atoms fill their K shells with 2 electrons, which is their version of an octet called the duplet rule. But the octet rule isn't limited to simple atoms or ions, it also guides complex chemical groups called polyatomic ions. Take the sulfate ion, SO4 Here, sulfur shares electrons with 4 oxygen atoms and each atom achieves a stable octet. In polyatomic ions, the octet rule is satisfied by both sharing and transfer of electrons with an overall charge balancing the whole structure. The ammonium ion, NH4+, is another example. Nitrogen shares electrons with 4 hydrogen atoms, and the entire ion carries a positive charge. These advanced examples show how the octet rule is the guiding force for stability, even in more complex chemical species. Like every rule, the octet rule has its exceptions. Some elements are stable with fewer than 8 electrons in their valence shell. Hydrogen, for example, is satisfied with just 2 electrons. This is called the duplet rule. Beryllium and boron can be stable with 4 or 6 electrons. Then there are elements that go beyond the octet. Phosphorus in PCl5, that's phosphorus pentachloride, holds 10 electrons in its valence shell. Sulfur in SF6, that's sulfur hexafluoride, holds 12. These exceptions don't break the logic of the octet rule, they just show chemistry's wonderful diversity. So, to wrap up, the octet rule explains why atoms bond, why compounds form, and why elements react the way they do. Whether it's the water you drink, the salt you eat, or the DNA in your cells, the quest for a stable octet underlies the entire story of chemical bonding. By understanding the octet rule, chemists design new materials, predict reactions, and even explore how life itself is built at the atomic level. I hope this session helped you see how chemistry is more than equations, it's the invisible force behind cooking, cleaning, fueling, and even healing. Catch you in the next class where we'll uncover more amazing secrets of the atom.